This is the fourth lecture of this week. In the first three classes, what we did is we briefly revisited some of the important concept of complex variable, which we require to formulate the problems in elasticity. That formulation, that exercise we will do today. So, today's topic is the complex variable formulation of elasticity problems. Okay. You recall when we discussed the formulation of boundary value problems in elasticity, at that time we had seen there are two kinds of formulation. One is the stress based formulation, where your primary variables are stresses. You have to determine stresses from the equations. And there is another formulation, displacement based formulation, where the equations are written in terms of displacement. We'll do the same exercise. We'll write those equations, both the formulation, but at that time those equations were written in terms of x, y, or in polar coordinates, say r theta. Now the equations will be written in terms of z and z bar. These are the two variables that we used in complex method. Okay. Now let us start with the stress based formulation. If you recall, if we combine the governing equations and then the compatibility equations and then define a potential, a stress function phi, which is called Airy's stress function as this, then the final equations we can have this biharmonic equation. If there is no body force, if we ignore the body force, neglect the body force, then this equation, the form of these equations as equation is same for both plane stress and plane strain problem. So, let us now write this expression. This is the biharmonic equation. Let us now write this same biharmonic equation in terms of complex variables. Okay. Now, you see, let us the biharmonic equation is essentially can be written as like this, right. So, this equation is essentially del 4 phi is equal to 0, okay. And del 4 phi is essentially your del 2 of del 2, where del 2 is the Laplacian operator, right. Now, so you recall these are the things, the relation between del x and del z and del z bar. We derived this relation in one of the classes in this week. Now, what is the let us find out del 2 operator. Del 2 operator is del 2 del x2 plus del 2 del y2, right. Now, let us write this del 2 operator in terms of z and z bar using this relation. Now, del x, so what it is? It is essentially, if we substitute del x from this expression, we have del z plus del z bar and then square plus del z. You recall we discussed that though if we know z bar is essentially conjugate of z, but here we treat z and z bar as independent variables. So, equations are written in terms of z and z bar. So, now this is square. So, this, if we combine this eventually becomes 4 del 2 del z bar. So, this is the Laplacian operator. So, del 4 operator then del 2 of del 2 and this essentially becomes the square of this. So, 16 del 4 del z 2 del z bar 2. Okay. Now, the biharmonic equation was del 4 phi is equal to 0, del 4 phi is equal to 0. So, this gives, if I write now this del 4 operator in terms of z and z bar. So, this equation becomes del 4 phi del z 2 del z bar 2 is equal to 0. So, this is the biharmonic equation. The equation that we had in case of in terms of x, y and or r theta coordinate, we already derived. This is the equation, the same equation written in terms of z and z bar. Okay. Now, the solution of this equation, then what we did in the case of in x y plane or in r theta plane, we try to find out the find out the solution of that biharmonic equation. Here also we do the same exercise. The solution of this equation, the phi, once we have the phi, then the phi will be related to stresses, and then stress. So, with the knowledge of phi we can determine stresses. Let us see how it is to be done in the case of complex variable approach. Now, so finally equation we have is, this is the equation, the biharmonic equation, the same equation now becomes this. Now, if we integrate this equation directly, if we integrate this equation, then that integrated, after the integration, the equation becomes, the phi can be written in terms of two functions, gamma and chi. Okay. You can directly just integrate it once. First you integrate with respect to z and then integrate with respect to z bar, and then you get this expression. So, that exercise, that derivation I leave it to you, that is also given in the book. Now, so if we, now you see z is what? Z is equal to x plus iy, z is equal to x plus iy. If gamma is the function of z, so gamma is the function of z, so gamma also can be written as gamma real plus I into gamma imaginary, right. So, that is how the complex function is written, real part and the imaginary part. So, if we assume, if we say that if phi has to be real, then there in this expression there will be some real part and imaginary part. If phi has to be real, then we can ignore the imaginary part, and then the phi will be real of the entire thing, real part of the entire thing. Okay. Now, so you see the real part of the entire thing, if you see gamma z, gamma z bar, if chi z, if chi z can be written as chi real plus I into chi imaginary. Similarly, chi of z bar can be written as chi real minus I of chi imaginary. So, if you add them, so only left with chi real part, that is why it is a chi real part, this is the real part. So, imaginary part goes and then you have essentially the real part. So, phi has to be real. Okay. So, this is for phi. We will discuss, these two potential gamma and chi, they play a very important role here. So, essentially what we have done here is, unlike the previous cases where the phi was written in terms of x and y on r and theta, it was just one function phi, but now what we have done here is the phi is written in terms of two functions gamma and chi. So, essentially the problem is reduced to finding these two constant, where in earlier cases the problem was to find out only phi. Here the phi is a combination of chi and gamma, we have to find out these two functions and their associated constant is to be determined based on the boundary condition. We will come to this point shortly. Now, once we have this, so this is for the stress formulation. So, similarly, if we have to do the similar exercise for displacement formulation, if you recall, this was the expression which is called Navier's equation, that is the equation written in terms of displacement, where u in this case, u is a vector. So, u is a vector. U is a vector which has two components u and v. Now, we have to write the same expression in terms of complex variable, okay. And del operator was, if you remember, del operator was del x and then del y, right. This was the operator. Now, u, let us define u, complex displacement is equal to u plus I into v. So, u and y, if you take u is in this direction, this is the direction of u, this is the direction of v, that was u and v defined. U is the displacement in say x direction, v is the displacement in y direction, and then if we define a complex displacement which has to be defined on a complex plane, in this case uv plane. So, this is u is equal to u plus I into v. Okay. So, for us equations to be written in terms of capital U, not their component. Okay. Now, so let us do that exercise. So, if we do that, if you recall this expression, this is the Navier's equation, and then if I write this expression in x direction and again in y direction, this will be the relation, right. So, since we are talking about plane problems, we have two equations, x and y direction. So, this is equation 1 and equation 2. Now, let us take equation 1 plus I into equation 2. The reason is, in the previous case, if you see, just now we wrote that u is equal to u plus I v. Now, we have to write this equation only in terms of capital U. So, these two equations which have in two directions, that equation needs to be combined and get just one equation. Now, this is how you let us combine these two equations. So, write equation 1. So, equation 1 plus I into equation 2. Let us see what happens. Now, if I write that, so this is the equation 1 in the previous slide, and then I into equation 2. Now, if you do that, then what we have here is, you see, so let us consider first this term and this term and this term. This becomes what? This becomes mu into del 2 of u plus I into v, right. So, these two term becomes this. Let us take the other two term. Other two term becomes lambda plus mu, and then del x of del x plus I into del y, and then del u del x plus del v del y, that is equal to 0. So, this is we have, right. Now, what is del 2 operator? Del 2 operator, just now we discussed that del 2 operator was what? Del 2 operator was 4 into del 2 by del z bar, right. So, this becomes mu into 4 del 2 del z bar, and u plus I v is u, that is how u is defined, okay, plus. Now, then we have this term. If you recall this expression where the relation between del x and del y and del z bar, this is the relation we had. So, this expression del x plus I into del y, that gives you 2 into del z bar. So, this becomes lambda plus mu 2 into, and this becomes del z bar. Now, similarly, if you substitute del x from this equation and del y from this equation and combine them, if you combine them, then you get an expression, final expression like del u del z plus del u del z, this is the bar. So, when we say del u del z bar, it means that del u bar del z bar, it is to entire this is the conjugate of the entire del u del z, okay, that is equal to 0. So, this expression you get by combining Navier's equation in both the directions, and then this is the final equation written in terms of z and z bar. So, the final expression is finally that this is the expression that you have, okay. Just now we derive. Now, similar to the previous case where the equations were written in terms of stress and we directly integrated it, let us do the same thing for this, and if you do that exercise, if you integrate that, then the expression that you get here is this. This is the expression we get. Now, you see the gamma z here, this gamma z is the same gamma z, that is, it is not a separate function, it is the same gamma z that we have in case of stress formulation. Now, then we have one more additional function which is psi z, there it was chi z, but this psi z and chi z are related to each other, and this relation is okay. Before that, there is a chi here, there is this kappa here. Kappa is for whether it is a plane stress problem or plane strain problem. Depending on that, you have this kappa. So, kappa, this value is for this for plane stress, and this is for plane. This is for plane strain, and this is for plane stress problem. And then the relation between psi will shortly come, psi and the chi that we discussed in the stress formulation. But again the same thing, the entire u is written in terms of two functions. So, essentially the problem whether you use displacement formulation or stress formulation, what we have seen, this entire thing is essentially reduced to finding these two functions gamma and psi. So, these two functions we have to assume, and these functions may have certain constants, and then these constants need to be determined based on the boundary conditions. Okay. Now, we will demonstrate that through few examples. So, summary, you see this is the summary, if you recall this, if you write the entire expression of phi, not just the real part, this is the entire expression of phi, and for stress formulation this is the entire expression for u, and the psi, and here this gamma z and this gamma z, this gamma z they are same. Only thing is this chi and this psi are related to each other, and that relation is this. Okay. So, once you do that derivations, integrate it, and you get that, you can get this relation. Okay. So, now then okay. So, then what we have? So, these are the things we have, right now, but still we are not in a position to before we apply these equations to solve problems, let us take this equation further and then see what this equation tells you about the stresses and the displacements. Okay. Okay. Now, you see, let us take this governing equation, this is the phi. You recall this was the relation of stress function with the corresponding stresses. Now, if I write sigma x plus sigma y, sigma x x plus sigma y y. Okay. Sigma x plus sigma y means this plus this. This essentially becomes del 2 del x 2 plus del 2 del y 2 of phi, right. So, this is del 2 of phi. Now, what it is essentially, the del 2 operator is what? Del 2 operator we have just now we have seen for complex variable, del 2 operator is 4 into del 2 phi del z bar. Okay. This is the del 2 operator. Now, phi expression of phi is given here, and if you substitute that expression in this equation, then what you get is sigma x x plus sigma y y, that is equal to 2 into, you can do this exercise, 2 into gamma dash z plus gamma dash z conjugate. This is the expression. So, this expression is expression number 1. You may be thinking that what is the use of this expression, why suddenly is taking sigma x x plus sigma y y, the why it is done, it will be clear shortly. Now, let us do this, take one more combination, that combination is say sigma y y minus sigma x x plus 2 I sigma x y. Okay. Now, this is what sigma y y is this, and sigma x x is this. So, essentially this become del 2 phi del x 2 minus del 2 phi del y 2, and then plus 2 into this. So, this becomes minus 2 I del 2 phi del x del y. Now, we know the relation of del x and del y with del z and del z, but with that relation, if we substitute, if you write the entire expression in terms of z and z bar, in terms of derivative with respect to z and z bar, and then substitute the expression of phi and do the derivative, you get the final expression, and that expression becomes this. This is the first expression which we derived, and this is the second expression for this. Okay. Now, so for the time being, just for a moment, so this is equation number 1, this is equation number 2. For a moment, application of this equation why suddenly in this form we write this equation, it will be clear shortly through one example. Now, if we do the same exercise for polar coordinate system, then what will happen? Now, if you recall, in Cartesian coordinate system, the stresses are written as this, right? Sigma xx, then sigma xy, sigma xy, sigma yy. The sigma xy and sigma yx same. That's why that because of the symmetry, the off diagonal terms are written same. Sigma rr, sigma r theta, and then sigma r theta, sigma theta theta. That is written in terms of polar coordinate system. Now, what is the trace of this? If you recall, when we discussed about invariance, trace invariance, the first invariant was the trace of the stress tensor. Trace of the stress tensor is sigma xx plus sigma yy. In this case, trace of the stress tensor is sigma rr plus sigma theta theta. Since this is I1, this is I1, the first invariant, first trace invariance. So, therefore, sigma xx plus sigma yy equal to sigma rr plus sigma theta theta. Okay. So, this straight away we can write. So, if we have to write this expression in terms of a polar coordinate system, so this expression, the first expression remain same, but only thing is that z is, instead of z we need to write in terms of r and theta. And if you do that exercise, the expression that you get is okay. Before that, the expression that you get is this. So, this is the expression for just now we have seen, this is the first invariant, and then this is the second expression. Second expression also become this, and this is how we write the displacement if it is written in terms of r and theta. Okay. Now, these two potentials, the first, the gamma and this psi, these two potential is called Kolosov-Moshkelishvili potentials. Okay. So, essentially our problem is to find out start with some assumption of this potential and substitute that potential in these governing equations. So, that and these potentials will have some constants, and then find out this constant, finding the relation between this constant through these equations and determine those constant. In addition to that, you have boundary conditions and determine those constants through these boundary conditions or any other conditions that you have in the problem. Now, before we actually solve any elasticity problem or detailed elasticity problem, just to get a flavor of the use of this form, use of this equation, let us take one example. Suppose a potential is given to you. Now, our job at the end is to assume the potential and then find the constants in that expression. But before we come to that point, come to actually solve boundary value problem, just to get a flavor of use of this equation, suppose a potential is given and that potential is say gamma z is equal to Az. A is the complex constant and psi z is equal to, say, psi z is equal to, say, b into z. Okay. Now, z is x plus iy, a is complex constant. So, a also have a real part which is ar plus I into imaginary part. Similarly, b is a constant, b has a real part plus then imaginary part. So, essentially we have four constants here, ar, ai, br and bi, the real and imaginary parts of both a and b. So, four constants. Okay. So, these potentials are given. So, let us write the stresses and displacement in terms of these constants. Then apply the boundary conditions of stress and the boundary conditions of displacement to determine this constant. For a given problem, suppose this is the potential given. Okay. Now, the first equation, if you recall, the first equation was sigma x plus sigma y, sigma xx plus sigma yy, that was equal to 2 into gamma dash z plus then gamma dash z conjugate. This was the equation, right. Now, gamma z is given here. So, this becomes 2 into a plus a bar. the conjugate of A bar. Okay. Now, A is AR plus IY. So, A bar will be AR minus I into A conjugate. So, essentially this becomes 2 into or 4 into this becomes 4 into AR, 4 into AR. So, this is our equation number say 1, equation number 1. Okay. Now, write then sigma x, the second equation if you recall, it was sigma y minus sigma xx, then plus 2 I sigma xy, right, and this was 2 into z bar and then gamma double dash z plus psi dash z. Okay. So, this expression probably we did not write in the previous slide, we did not show in the previous slide, but if you substitute the expression of del x, del y in terms of del z and del z bar, essentially you will be getting an expression similar to this. Now, what is this becomes? You see, this becomes if you this will straight away will be 0 because this is a first order is a linear equation. So, essentially what you have psi the first derivative of this. So, this becomes first derivative of this becomes b. So, this becomes 2b. So, this is essentially 2 of b real part plus I into imaginary part. Okay. So, this is equation number 2, right, equation number 2. Okay. Now, you see, now look at this, we know this property of complex variable that if we have x 1 plus I into y 1 is equal to x 2 plus I into y 2, then if we compare the real part and compare the imaginary part, this gives us x 1 is equal to x 2 and y 1 is equal to y 2. So, real part should be same and the imaginary part should be same. So, in this equation, in equation 2, if we compare the real part, what are the real parts? So, this is here left hand side, this is the real part and corresponding real part is this, and this is the imaginary part and corresponding imaginary part is this. So, compare the real part and the imaginary part, what we have is sigma yy minus sigma xx, that is equal to 2br, and if we compare the imaginary part, this becomes 2 sigma xy, that is equal to 2bi. And from first equation, if you compare the real part and real imaginary part, there is no imaginary part here, here also there is no imaginary part. So, we have sigma xx plus sigma yy equal to 4ar. Okay. Now, you see, if we, so this is equation number say eventually, so this is equation number say 3, equation number 4 and equation number 5. So, if we solve equation these 3 equation, equation number 3 and equation number 5, then what we get is we get sigma x, if we solve them, then we get expression for sigma x and expression for sigma y, and from equation number 4 we can get expression for sigma xy. Now, you see what advantages we had here. If we write this expression in terms of, that is the reason why this particular combination was chosen. Now, from the first expression, if we compare the real part and real part, we get sigma x plus sigma y, and if we come from the second equation, if we compare the real part, we get sigma y minus sigma x, and these two gives us 2 equations. From here we can determine sigma x and sigma y. And then from the second equation, if we compare the imaginary part, we get sigma xy. So, this, if you solve them 3, 4 and 5, these equations straight away give you sigma xy is equal to by. So, this is first equation, this, and then if you solve this equation number 3 and 4, similarly you get expression for sigma xx and sigma yy in terms of AR and BR. Now, once you have expressed sigma xx, sigma yy and sigma xy in terms of these constants, in order to determine these constants, you need boundary conditions. There will be some stress boundary conditions given. Suppose, for instance, if we say that it is all, if the stress is constant everywhere in the domain. If the stress is constant, then sigma xs, sigma yy all are constant, and that value if you substitute here, you get these constants for br, bi and ar. So, whatever information you have about the stress boundary condition, you can substitute that and get this relation of sig br, bi and ar. Now, do the same exercise for displacement. If we do the same exercise for displacement, you recall what was the displacement formulation. Now, displacement was the expression for the Navier's equation was something like this, 2 mu u, that was equal to kappa, which depends on plane states or plane strain formulation, gamma z minus z gamma dash z conjugate of this minus psi z conjugate of thing. And then here what we have is, we have gamma z is equal to az and psi z is equal to b, psi z is equal to bz. Now, if we substitute this here, then what expression we have? Now, let us write that expression. So, this is equal to 2 mu, u can be written as u plus I into v, and then you substitute gamma z here, and then if you substitute gamma z here, so what we have k, gamma z is equal to a into z. So, this becomes a into z, and then minus z into gamma dash z conjugate. So, this becomes a bar conjugate of a bar, and then minus psi z is this. So, this becomes b z. So, enter this thing. Okay. So, if you write a in terms of a bar and b bar, so essentially if you write z is equal to x plus I y, then eventually what you have is, just I am writing the expression, you can check it, a r plus I into a I, this is a written, and then z becomes x plus I y. So, this is the first expression, and then the second expression becomes minus x plus I y is z, and then a bar is a r minus I into a imaginary. This is the second equation, and the third equation becomes your b bar is b real minus imaginary, and then conjugate of b and conjugate of z minus I y. So, if you simplify this expression, then you get some real part and then some imaginary part, I into imaginary part, right. Then what is left? Compare the real part and compare the imaginary part. So, this gives you 2 mu u, that is equal to real part, and then 2 mu v is equal to the imaginary part. So, these two are the equation. These two are the equation number 1 and equation number 2 for displacement. Now, in real part and imaginary part, what you have, that real and imaginary parts are written in terms of some constants. Okay. Now, you have some boundary condition, the boundary condition specified. Now, if we substitute that boundary conditions, we get this constant. Okay. So, you see, the objective of this exercise has not been to really solve any boundary value problem. The objective of the exercise that just now we have done here, to tell you or to try to convince you why this particular form, the sigma xx plus sigma yy and then sigma y minus sigma xs plus 2y sigma xy, that particular form is written, that particular form is used, because this is the application of that, this is how this particular form can be used and can ease our problem in finding or in solving this equation. So, next class what we do is, next class we will start with this, and then we use all this formulation that we have written today, derived today, and then we do some examples of boundary value problems, where we see how to assume that in this example the potential is given, that gamma z and psi z. We will see what are the possibility, how it can be assumed, okay, whether it is a polynomial or different kinds of function. And then for a given problem, we assume a potential, and then that potential will be having some constants. We'll determine do this exercise and then determine those constants based on the boundary conditions specified. So, next class the topic is complex variable solution for boundary value problems in elasticity. With this I stop here today. See you in the next class. Thank you.